Hi, and welcome to this talk. My name is Christopher, and I'm here to present to you a recently published paper by me and my colleagues. Please reach out to me via email if you have any questions, and please also check out our GitHub repository where we have made available all the code and scripts and detailed output from this publication. As a clinician in psychiatry, I've met many patients who don't respond to our treatments. One approach to this dilemma would be to identify predictors of treatment outcome. The simplest way would of course be to have any self-report or any other behavioral measure to accurately predict treatment outcome. However, these attempts have commonly failed in research. Functional magnetic resonance imaging, bold fMRI, have shown promise, but I also think we need to be self-critical here and acknowledge the fact that standard fMRI measures have shown low reliability both in task and resting state fMRI. I believe we need to identify a different approach. Fluctuations in brain signals, they may appear to be random, and these variations across time, they typically are considered to be markers of noise. However, we also know that recordings of single neurons demonstrate trial-to-trial variability, and that this variability is not only related to measurement noise. In fact, moment-to-moment fluctuations in brain activity, as measured with fMRI or EEG, have shown to be a viable index of an individual's adaptability and effectiveness. And interestingly, cognitive performance have repeatedly been linked to moment-to-moment variability in the bold signal, as measured with fMRI. In this study, we are focusing on 45 patients with social anxiety disorder, and they all provided self-reports and diagnostic interviews before and after they underwent a 9-week cognitive behavioral therapy delivered via the internet. This is a standardized treatment that fits very well in research where we want to have control over as many variables as possible, and we also report high compliance to this treatment protocol. The patients answered a 48-item questionnaire named Leibovitz Social Anxiety Scale, and they answered these questions at multiple time points before and after the treatment. Before they started the CBT, they underwent 2 fMRI sessions. We refer to these as baseline 1 and baseline 2, and in between we had an 11-week period of waiting period. And we did this to establish a test-retest period for the 2 fMRI sessions. After the second baseline, patients started the CBT, and we measured symptoms and social anxiety after the treatment. Within each scanning session, patients underwent a repetition suppression task for 3 minutes. This task consisted of 2 blocks. One block of 80 seconds where we showed one face on the center of the screen, and this facial expression was presented repeatedly over these 80 seconds and was blinking on the screen. After this block, we had a short period of a fixation cross, and hereafter we started the second block with a different face presented on the screen for 80 seconds. This procedure and task was then repeated at the second baseline 11 weeks later. We had 2 different facial expressions in this task, either a fearful face or a face expressing happiness. In addition to this repetition suppression task, patients also underwent a resting state scan for 6 minutes. The typical approach in bold fMRI research is to establish each voxel's average activity across time within the task. We refer to this as the mean bold approach. Here we are more interested in the variability, so we define each voxel's standard deviation across time. We refer to this as the SD bold, And by doing so, we establish the moment-to-moment variability at the level of each individual and each voxel across the whole brain. We used a reliability-based cross-validation approach. Basically, we use a partial least squares model to linking brain to behavior at the first baseline. And this means that each voxel across the whole brain represent the weight between the brain data and the social anxiety change score. We applied this weight to the second time point. So we have data collected 11 weeks later. So the weights from the first baseline applies to the data at the second baseline. We calculate the latent level brain score, basically using the dot product of all those weights from the second baseline, and these brain scores were subject to a five-fold cross-validation in order for us to achieve a predicted change score that we could compare to the actual change score that each patient displayed. We're interested in horse racing brain and behavioral measures in this study. And we do this by comparing accuracy in treatment prediction and test-retest reliability. So first, we want to know if the neural response can predict treatment response better than any of the self-reports included in this study. Secondly, we want to test this good old Sampson model, the good old mean bold model that we've used for many years, to a more novel approach looking at the neural variability, here referred to as the dynamic DUG model, where we have a face task SD-bold model. But we're also interested in comparing this task as compared to a common resting state scan, where we also calculated the standard deviation across time throughout the scanning period. And I refer to this model as the Lazy Louis model of resting state variability. And we're also interested in knowing how much time we would need to get a reliable prediction of our outcome, 40, 80, or 160 seconds of scanning period. First, our patients did drop in social anxiety from, on average, 77 to 43. This represents the Cohen's-d within group effect size at 1.62. We found that the face neural variability did predict the treatment outcome, and it did this at Pearson R at 0.65 between the actual change score that the patients demonstrated with the predicted change score using the face task variability measurement. We found that low variability in the visual cortex and high variability in prefrontal and temporal cortices were linked to better treatment outcome. And interestingly, when we combine the face task SD-bold with the resting state SD-bold and the self-reported anxiety measure at pre-treatment, we did improve the prediction performance slightly, with a Pearson R at 0.77 between the actual change score and the predicted change score using these measures. However, we also found that the shorter task SD-bold measurement showed the largest proportion of explained variance when we compared these measurements. And the task SD-bold explained variance was more than doubled, almost doubled, than the longer resting state SD-bold scanning. And interestingly, the task and resting state are also different when we look at the spatial pattern across the whole brain. So the variability in the task and the resting state were very dissimilar. Another way to look at this data is to look at the prediction errors. So on this mean absolute scaled error, a lower value means a better prediction. And here I demonstrate to you the task SD bold in yellow. We have the resting state variability in brown, and in beige we have the task good old mean bold approach, and in red we have the self-reported social anxiety symptoms. And below here we present the different models in seconds. So basically we're showing that even a model with 40-second scanning of the variability of the task was sufficient to accurately predict the treatment outcome. The variability for resting state did also predict the outcome, but we needed almost the double time to achieve this prediction. The shorter times with the resting states was not sufficient to predict the outcome. And the conventional mean bold approach did not achieve any accurate prediction at all. Basically, we are showing that standard mean bold measurements was poor in prediction performance. Variability in resting state was only predictive at longer scans, and the task SD-bold outperformed both resting state SD-bold and the conventional task mean-bold approach. When we look at the 11-week test-retest reliability of these predictions models, we can look at the literature, and there are currently 2 meta-analyses that I'm aware of. Noble et al. 2019, looking at functional connectivity and commonly resting state scans with the intra-class correlation coefficient around 0.3. Another study by Elliott in 2020 looked at task-related test-retest reliability, and the ICC was about 0.4. In this study, we found that the task variability model showed test-retest reliability in 11 weeks, starting at 0.6 and peaked at about 0.8 for the 160-second long task model. The resting state variability model did not achieve as good reliability as the task model, but when we did improve the length, or when we extended the time for the resting states to almost the double as compared to the task, resting state variability was as reliable as the shorter task. We can also look at the 11-week test-retest reliability on voxels and clusters. So on the cluster level, the clusters who appear to be predictive of the treatment outcome, first the task SD-bold showed a good test-retest reliability, here indicated with Pearson R ranging from -1 to +1, and the diagonal line represents a good relationship between the two measurements. Similar for the SD-bold resting state, whereas we cannot see this for the mean-bold task approach. If we look across all the voxels across the whole brain, here with Pearson R range across the whole brain, we also find for the 2 variability measures on the task SD-bold and the task resting state SD-bold to find high correlations between the 2 measurements time points. And for the mean bold task, we found much less reliability between the 2 time points. And this is also nicely plotted in the histogram here. So to sum up the findings in our study, we found that neural variability as compared to mean neural activity, that the SDBOL dominated the standard approach in this task-related activity. And it dominated the standard approach both related to test-retest reliability over 11 weeks and accuracy in predicting therapy outcome. The neural variability is commonly disregarded as a noise, and for instance commonly used in signal-to-noise ratio calculations. But I think we might have to rethink our measurements that we are typically using in standard fMRI. As we showed here, the investigation of neural variability could boost the effects and accelerate the potential application of brain imaging in clinical psychiatry. We also found that the shorter phase task outperformed the longer resting state scanning, and it did this as being the strongest predictor of treatment outcome, but also with the excellent test-retest reliability. Resting state did perform, but it did require more than double the time in data volume. And also the longer resting state, even though it did the job, it accounted for about half of the unique explained variance as a predictor of treatment outcome. I believe that us as neuroscientists, we should focus on developing disorder-relevant tasks, and that we should focus on neural variability being a strong candidate for future smaller and larger scale investigations in psychiatric biomarkers. Treatment-responsive social anxiety disorder patients, they did express a more limited variability in visual cortex. And this is in alignment with the idea that people and individuals with a less accurate processing of incoming stimuli also demonstrate low variability in the visual cortex. And we also found that patients who displayed a higher variability in the prefrontal cortex, they profited more from cognitive behavioral therapy. And this is in alignment with the idea that greater bold variability in the frontal lobes are usually seen in healthy, higher performing adults across a host of different tasks, such as in attentional capacity, in working memory, and also in verbal abilities. Of course, there's a number of limitations to this study, and there are a number of questions that needs to be addressed in the future. First of all, this study did not show and did not achieve out-of-sample prediction. We found a treatment outcome prediction model that was reliable between 11 weeks of test-retest. And we of course would like to know if this model can generalize to any new patients coming into the clinic, and we obviously would need much larger sample to address such question. We used a social anxiety relevant task in this study, and we compared this to resting state, but we did not have any other task unrelated to social anxiety, such as a motor task. So this is something we would very much like to include in a future study. And of course, as a clinician, the most important question here, we need to not only predict who will respond to one treatment. Of course, we need to know what treatment to allocate to an individual. So we basically need to predict the treatment modality. Is it therapy A or therapy B that is supposed to be recommended? I believe that we have demonstrated evidence for the moment-to-moment neural variability not being only noise. Instead, this variability offers us some unique insights into factors that affect patients' responses to psychiatric treatments. I believe that the disorder-relevant and task-based neural variability could be a key for future directions in neuroscience-based psychiatric research. And I think it may be that we can, with this type of model, improve clinical decision-making and precision medicine. I really want to take this opportunity to thank all the people that have been involved in this study, all the students and staff who supported the data collection, Umeå Center for Functional Brain Imaging, where we conducted all the scans, and also a number of funding agencies who enabled us to spend all this time in this effort, and of course a warm thank you to all the participants in this study. Thank you very, very much. Thank you very much for your attention. As I said in the beginning, please contact me via email, and also check out our GitHub repository for more information. Thank you for your attention. Bye bye.